All right, hey everyone, welcome to HoTT, and our speaker today is Håkon Gylterud, and he will speak about defining and relating theories.
Thank you, and thank you for having me on. I'm currently in Bergen, and we have rain today mostly. And I'm actually on parental leave, but I'm taking a break from changing diapers to come and talk to you about defining and relating theories, which sounds a bit vague, but hopefully this will be a nice and concrete and opinionated take on this. The motivation for this is several things. But one of the main motivations is that I want to make a kind of software framework for working with theories and translations between theories, like logical formal theories of the kind which type theories are an example. And so the plan is that we'll look at some examples of theories and rules and try to give like an overview of what I mean when I say theory. And then we'll discuss a bit how to represent these in a combinatorial fashion. And so that's sort of the focus on this. And then we'll look at the software project called Myott, which is written in Haskell, and it's meant to be both like a standalone specification tool where you can write in some language the specification of your theories and specifications of translations between theories. But also as an API for like advanced usage of this, where you want to have more control over what's happening and be able to extend with your own functionality. So it's currently very much a prototype. It's not actually usable yet, but hopefully that will change in not too far into the future. And then I'll round up with discussing a bit about where this is going and what I'm planning to add to this and so on. So, like I said, Myott is meant to be a standalone specification tool for theories, which means that if you have like an idea for a theory and you want to experiment with writing down the rules and check that the rules are coherent, make sense in relation to each other, and want to try writing out some proofs in that theory, and then try to relate those theories together by providing translations between theories. So that those kind of things are what we want to do in Myott. And then there's also, well, I'll demonstrate this a bit, like an Haskell API for writing Haskell code, which manipulates theories and does things with it. There's a link there down below to the repository. Probably pointed the wrong way there. And you can check it out as far as it exists. I'll give an overview of the code a bit later. And the motivation for trying to define this kind of general notion of theory and writing this piece of software is that we have currently a multitude of different theories. So I mostly work in type theory, but type theory actually is not one theory, as we know. It's several different theories. Even before homotopy type theory happened, we had different kinds of inductive families, induction recursion, and different variations of type theory going on. And then when we got homotopy type theory, we got a lot of different theories. Suddenly we have higher inductive types, cubical type theories, modal type theories, and so on. And then there are all other kinds of theories as well. There's set theory, there's first order logic, higher order logic, category theory, although we don't usually think of that as a kind of formal theory. We could specify that as formal theories as well. Linear logic, and then there's software specification, where in software specification you have a lot of different theories which treat different things, like formal theories for version control systems or formal theories for editors. So there's lots of examples of formal theories there as well. And we have all these theories, and I'm sort of interested in the relationship between these theories. In particular, I worked a lot with the relationship between set theory and type theory. And all of my time has gone into working with models of set theory inside type theory. And when doing that, one sort of thinks of these two things as living on an equal level. So there's set theory and then there's type theory. And the question is then, in what sense are these both theories? Right? In what formal way are these theories, and how do we relate these? The sort of classical answer to the question, what is a theory, is that a theory is a set of theorems. Where theorems is some set of formulas or strings of some language, and then a theory is just a set of these. But that doesn't explain enough to sort of actually implement this in software, and it doesn't make a very satisfactory formal definition either, at least not from a type theory perspective. So it doesn't explain how do we define theories. It doesn't explain what a theory is about. So that's something I want built into this notion of theory, is that it should be about something. And it doesn't explain how to relate different theories. So for the sake of implementing Myott, and also for sort of, theoretical reasons, I want an opinionated notion of theory which settles these kinds of questions. So this is work in progress, but hopefully I'll be able to get across ideas for this. So just to have a concrete example of what kind of things I would like to have done is that, say we're working on modeling set theory in type theory. So set theory is a theory, type theory is a theory, and we would like to have a translation of set theory into type theory. And we know how to do that. We know that, for instance, when we interpret the existential quantifier in set theory, we have a choice. We can either interpret it as a usual sigma type, or we can interpret it as a truncated type. And then we can define these two different translations. And in each case, it's obvious how to define the translation. But if we want to formalize this, then either we have to, and this is what we usually do, we have to carry out those translations by hand and specify them for our model. So we take the axioms of set theory and we by hand write out what is the corresponding type for each axiom. And then we give a term of that type for each axiom. And then we say, okay, I proved it. And then we put that into Calc or Agda and so on. Or we could do it all internally inside type theory, because type theory is a very powerful theory where we can define the type of all formulas of set theory. And then we could define a sort of encoding family which decodes each element of that type to a type, and then we could apply that family to the axioms and prove them. But these are a bit unsatisfactory, both of these. So doing it by hand is certainly unsatisfactory, and doing it also internally in type theory feels also a bit like cheating, because we're sort of exploiting the fact that type theory is able to represent everything and do everything internally there. It doesn't feel like set theory and type theory are sort of on equal terms from that perspective. So a bit about related work before we get going. So the first inspiration is some of Per's early work on models of interstitic type theory, in particular his 75 paper about models of internistic type theories and the notion of definitional equality. But perhaps an even greater inspiration is Cartmell's notion of generalized algebraic theories, GATS. which where one could see what I want as sort of a generalized algebraic theories with binding operations on them, if that makes sense. But also, I want to take a slightly less syntactic approach. If you read Cartmell's thesis, you will find that it's a quite syntactic approach, after all. I want something which is more combinatorial in the sense which Makkai's first-order logic with dependent sorts are combinatorial. So I'll go into a bit of the details about Makkai's notion of dependent sort vocabulary in a moment. Yeah, and also very related to this is Andre Bauer and Hasselwater and Lumstein's work, which I don't know, maybe Peter has a good reference for this, but his talk last summer, What Are We Thinking About When We Present a Type Theory, is sort of very much in the same manner as I want this to be, only that they present a notion of what a type theory is, while I would like something slightly more general where you're free to have other kinds of judgment, not just something is a type or something is an element of that type, but rather have any kinds of interdependent kinds of judgment. Then there's also Uemura's abstract type theories. And finally, Lumstein and Subramanian's dependent operads, which comes very close to the notion of operation, which I'm going to talk a bit about today. But they also are also based on Makkai's dependent sort vocabularies or inverse categories as the foundation for their signatures. So, in sort of trying to get at what I mean with the sort of general theory, I sort of divided it up into these parts, where we'll first talk about judgment forms, which is what you start with when you specify your theory. You say, what kind of things is my theory about? And the thing is that they might be related to each other as sort of dependent sorts and relations. And then once you've defined what your theory is talking about, you either go ahead and if it's a sort of algebraic theory, you specify its operations, or if it's some kind of logical theory where you typically have operations which bind variables, you go ahead and you specify rules for that theory. And then once you have theories, you can translate between those. So that's the idea. And in each case, we want a kind of combinatorial sense to these notions. And just to be a bit more specific about that, what I mean by combinatorial, let's have a look at the following diagram. So here we see, this is kind of a sketch. So imagine that we're trying to, with our theories, we're trying to model how a mathematician is working. So at some point, a mathematician has reached sort of state gamma, where his state might depend on what theory he's working in, but the state gamma is meant to be a sort of set of all the objects which the mathematician has created so far. So we can think of it as a context or environment in which we're doing our derivations. And then we could do one of two things. The usual way is that we have a context as with just a list of our assumptions. And then when we extend the context, we add an additional assumption. And in that sense, we're we're extending the context. But we can also imagine that we extend the context whenever we apply a rule or an operation to construct a new mathematical object. So that we sort of, the context doesn't contain all the possible things we could construct in it, but it contains only the things we actually have constructed so far. And then we want to apply a rule. Our rule here is called R, and the rule has some presumptions, some assumptions on the top, and then it leads to some kind of abstract conclusion. So this is the rule part, is the inclusion of the premises into the premises and the conclusion. And then we have this alpha, which specifies how we want to apply the rule in this particular case. And then once we've applied the rule, we get a push-out diagram, and we get gamma extended with this new application of this rule. So this is a push-out diagram, and it's sort of dual to how we do things in sort of categorical semantics of type theory, where we do pullback diagrams to represent substitution. We sort of just turn things around so that context extensions go the other way. And the idea is that both assumptions and both making a new assumption and constructing something in the context you're in is a push out. And this creates a sort of, Peter Lumsdaine emphasized this nicely in the summer, that you get a sort of cell complex view of adding new things to your current context. Whether that context, and that context can be either just things you've constructed or sequence of reasonings you've done so far, where each sequence is something with some assumptions and some conclusion. Or it's a whole set of rules. Okay, so that's the, and the idea here is that, or rather the question is, what are these objects? What kind of things are these objects? And the idea will be that they will be kind of finite sets with some extra structure imposed on top of it. Some kind of, so in the case of just having the sort vocabulary specified, only the lower level here, judgments, in that case, these things will just be presheaves, set valued functors. But once we add more structure, these things get more complicated. Okay, so some examples of theories. So we start with type theory. So type theory, as we know, has 4 judgment forms, 4 kinds of judgment. And that's being a type, being an element of a type. And you see here, I spell out specifically, so there's no no coercion from being a type to being sort here. And then there are definite or judgmental equalities between types and judgmental equalities between elements of a type. And there are a couple of things we can notice here. The first thing we notice is that the last 2 here are kind of propositional, in that here we talk about A being a type, here we talk about little a being an element, while here there is no new variable introduced. A and B sort of already existed, and we're just talking about their equality. And the same with here, A and A prime already existed, and we're just talking about their equality. So no new variables are introduced, or these are propositional. Next thing to notice is that each judgment kind comes with presupposition. So for instance, being a type doesn't have any presuppositions, but being an element of a type presupposes that the thing we're an element of, that I already forgot element, presupposes that A is the type. And the same with equality, this presupposes that A and B are types. The judgmental equality presupposes that A is a type and that A and A prime are elements and so forth. So these presuppositions or the boundaries of the judgments are going to play an important role. Let's just pick another theory. So let's say we're working inside a particular category. Then we would have another set of judgment forms. We would have being an object, being a morphism, and maybe also equality between morphisms as our judgment forms. And again, for those forms of judgment, we would have presuppositions. So, for instance, being a morphism presupposes that A and B are objects, and an equality presupposes that the things are actually morphisms between the same objects. Final example we'll have a look at is set theory. So one might have expected set theory to have judgment forms. A is a set, A is an element of B, and A is equal to B. But when we formulate set theory, we formulate certain axioms, such as separation. We formulate them in terms of formulas. So formulas are actually an integral part of set theory. So instead, we will have A is a set, A is a formula, and phi is a formula, and phi is true as judgment forms for set theory. And we see here there are not that many dependencies because this is basically a first order theory which has sorts and formulas. But dependencies sort of play a role there when we get into the rules. So elementhood would then be a term forming operation, which says that whenever A and B are sets, then A is an element of B is a formula. So in each of these theories, we have a set of judgment forms, and some judgments are propositional and judgments have presuppositions. So that's the general setup. And the really nice thing about Makkai's first order logic with dependent sorts, so there's several nice things about that, but one of the cool things in the beginning is that he says that these kinds of structures can be captured as some kind of categories. That's Makkai's dependent sort vocabulary. So what's that? Well, a dependent sort vocabulary is a pair. It's a category, and it's not just any category. It's either finite or it has a finite out degree, depending on how strict we want to be. And I think in Makkai's setup, they are always finite, but we could easily imagine these go on to infinite things. We'll have problems representing that on a computer, but in theory that would work. But and then there's an extra constraint on this category, namely that the existing and non-identity arrow relationship should be well-founded. So that means classically that there are no infinite descending chains of non-identity arrows. And then this P is a set of maximal elements. The maximality requirement is not essential, but if you want to add non-maximal elements, then you'll have to add some more constraints, but I'll not go into those details. But this set P represents the judgments which are propositional. So the idea here is that the objects of C represent judgment forms, and the arrows represents the presuppositions. And so the sort of, if you look at a specific judgment form as an object and you look at all the arrows out from that, that sort of forms the context of that judgment form. We'll look at examples in a moment. And then P is just a set of those which are propositional, so like equality, for instance, in the previous ones. So here's an example where we take the category judgment signature, where we had, now I'm phrasing it a bit differently. Now I'm phrasing it more closely to the syntax of the software, which I'm going to go into in a moment. But the first one says that object is a kind of judgment, namely a sort judgment. And then if x and y are objects, then hom_xy is also a sort judgment. And then if x and y are objects and f and g are morphisms from x to y, then f equals g is also a judgment, but now it's a propositional one. So the corresponding dependent sort vocabulary, this category, is the following category, where we start by adding one object for each of these lines. So we have one for object, one for hom, and one for equality. And then we add arrows representing the various dependencies. So for instance, for hom, we have an x arrow representing the x object and a y representing the y object. And these go into object because both of these are objects. And then for equality, we add the f and the g, they are homs. And by composition now we already have, we take this graph and then we take the free category on that, and then we quotient out by some equations. So on the equations we quotient out by is saying that the x, which is mentioned in f, is the same as the x mentioned in g, and the y when mentioned in f is the same as the y mentioned in g. So that those two compositions are equal. And then we end up with a category, and this category it's directed downwards, and it's there are no infinite chains. There are no loops. This is a finite category, so the same. Having no infinite chains is that there are no non-identity loops in this category. And we could rename a bit, so to make it this even more semantical, or like even more natural. So if we rename the x and the y here to domain and codomain, and then we rename the f and the g to left-hand side and right-hand side, and otherwise just keep the same signature, we just rename the variables. Now we get the same graph, the same category generated, but now that we see that the equations make even more sense in the fact that for us to compare two arrows, we need the domain of the left-hand side. Oh, I switched things. I wrote things wrong. No, it's correct. No, sorry, it's correct. No, the domain of the left-hand side should be the same as the domain of the right-hand side, and the codomain of the left-hand side should be the same as the codomain of the right-hand side. That's a way to read these equations so that they make sense. All right, so from this this kind of signature of judgment kinds of this theory, we get a category. That's Makkai's dependent sort vocabularies. We'll do another example, namely the judgments of type theory. We just saw them. They was type judgment and element and equality between types and equality between judgments. And we get in the same way a category now with 4 objects and a similar requirement, namely that the type mentioned in for A is the same as the type mentioned for A prime. And we can again do this kind of renaming to make it even more readable. So if we rename the first A here to type of, whenever we have a type of, which is a type, then element of type of is a sort. And then then we get here that for equations that the type of the left-hand side has to be the same as the type of the right-hand side when we compare elements judgmentally. Yeah. Okay. So.
Sorry, can I ask a question at this point?
Sure.
So I would have thought in interpreting the judgments of type theory that the judgmental equality between types would also be a proposition and not a sort. I understand that that's prohibited by Makkai's formalism, but I was wondering if you could comment about that.
Oh, it's actually meant to be. Yeah, that's actually a typo for my the drawing sort of tries to say this by making this blue, but yeah, it's supposed to be a proposition as well. Yeah.
Okay, well then maybe I'll change my question.
Okay.
My memory of Makkai's formalism is that the only objects in his, inverse indexing category that are permitted to have, relations on them as opposed to further types that depend on them are the maximal ones, and type is not a maximal thing in this indexing category. So,
so I think the requirement, we could check this, but I think the requirement is that the relations are supposed to be maximal. Not that the relations has to be on maximal things, but maybe I'm also.
Oh, I was confusing. Well,
so right, the ones which are propositional are the ones on the top, not that they have to be on things which are on the top.
Okay, thanks.
Yeah. But we
Makkai does have a special treatment of equality, which maybe what you're thinking of.
Yeah. That is what I'm thinking of. And of course, this is an equality relation, but maybe it's not specially treated as an equality relation.
Yeah, no, this equality is not specially treated. I would like to add some specially treated equality later, but that's to do. Yeah.
Great. Thanks for the reminder.
Yeah. And actually, it should be possible if you add some additional requirements to have propositional things in Makkai settings, which are not maximal. The reason they are maximal is because when things depend on it, they could be more than one dependency, and it could be sort of incoherent in the category. But I think you could add an extra requirement. That's beside the point, I think. Okay, so now I wanted to have a look and see if I can change the setup here. At how Myott currently specifies judgments. Let's see, I can find my window. Not that one. Just a moment. I'll just precise it so that it hits the screen. Just a moment. And set it up in advance, but somehow it got lost. Here we are. So, so this is the specification. Oh, now I see that it's missing the top. Let's fix that. All right. So here is the specification for the theory of a category, but only the judgments here. So it says that ob is a sort, and then dom is, if dom is an object and codom is an object, then hom is a sort. So you see that there are no mentions of hom of the variables here. And that's something I want to use that later, that space to represent which variables are hidden and which ones are not, but currently hidden variables are not implemented. So So there's nothing there at the moment. All variables are visible by default. Yeah, and then equality between arrows. And then, so you see the syntax of Myott is meant to be like very closely to what we would write informally here. And then I wanted to dig into the source code. Let's see, let's jump to the top. So here's the HoTT, which is not complete yet, but there's a HoTT for the Myott framework. And I wanted to go into judgment, just sort of point out how these are represented in a kind of, it's not exactly, it's not phrased as categories and dependent sort vocabularies directly, but it's also based on sort of finite sets representation, which is sort of just specifying the category in a slightly different way. Let's look at the source. So variables are just identifiers. Judgment forms are also just identifiers. But then there's this distinction between a sort judgment and a propositional judgment. And then a judgment is just the name of the judgment which you're calling upon. And then it has arguments. And here we see that's kind of finite sets representation, which where it doesn't have, at this level, it doesn't work with the abstract syntax. It works with maps of finite, as a sort of inductive type, it works on it as with maps between finite sets. So there's a set of the map from variables to variables, giving you the arguments of each judgment. And then you just, a bit for convenience here, also remember what kind it was when you specify. And then a context just maps each variable to a judgment, so that the things we saw on the, let's see, can I switch between those? Yeah, I can. So the things we saw here, these kind of contexts here are finite maps. Mapping variables to their judgment. And then a specification is just a map from each kind of judgment form into a context and their kind. So this is sort of the pair here is the sequent where you have the context on the left and the kind of judgment. So say is a sort on the right. And then these are just the combinatorial representations, and that you could have elements of these data structures which do not correspond to a coherent theory, where you could have things where things are incoherent. So then there's a kind of kernel, which I've called referee. Here it's a kernel whose job is to verify that these are correct. And you feed them through this interface. That's a trick I learned from Andre Bauer, to use these abstracted types instead of the specific types, and then using an interface so that when you proof check, you can't inadvertently trick the kernel by giving some invalid state at some point. You have to, the states is abstracted by these variable types. So you have to work with that in an abstract way, which prevents you from cheating, so to say, when talking to the kernel. And then you initialize with an empty specification. In any specification, you have an empty context. And then in a specific specification, you can extend it with a judgment kind to a specific context to say that there's a new judgment kind in that context, and then you get a new specification. Or you can, when you have a judgment form, a judgment, you can assume that there is something of that judgment in that context, and you get an extended context. And the reason you just have to give a judgment, you don't have to give the context there, is because every judgment is relative to a context. So you have these dependencies function here, giving you, for every judgment, the context it was created in, and in every context, the specification that it was constructed from. And then apply is how you create new judgments in a specific context. You provide just a map which tells you what the value of different arguments are. So for instance, if I want to create a judgment form hom xy, I would give the map which sends the element domain to x and the codomain to y. And then the kernel will check that that makes sense with respect to the definition of hom. Okay, so that's the interface for the referee. I will not go into the implementations of this, but it just checks in each case that things make sense. So that when we go back to the thing, we can test it, hopefully. Run a test, and we'll see down here. It now checked that this specification works. There's not really that much which could go wrong here. We could, for instance, forget to give an argument to say hom. And in that case, it would say something like, in the definition of equality, when checking the well-defined things in the category examples cat.j, the judgment hom takes 2 arguments but was given 1, for instance. So it will do like checking of those. Okay, so in addition to this kind of you write and it checks kind of interaction, we also you can also interact with this in a sort of monadic fashion as an API. Let's see. Let's go back to judgment. Now let's go to the examples. So for instance, here's the same specification, just written out in this kind of monad fashion, where you say, okay, this is specification, declare object to be a sort in the empty context here, and declare hom to be a sort in the context where we assume that domain and so on. So this is just spelled out in this monad, the same things we had in the thing. But we'll see when we get to operations that since this is now happening inside Haskell, we can write some code to do some things which we can't do from the source code just yet. Okay, so there are those were examples. Let me jump back to my presentation here. And we'll pass on to operations. So, so for instance, categories can be formulated as a generalized algebraic theory, and the operations are taking an object and turning it into its identity morphism, and or taking 2 arrows and composing them. And so we could see, so that's not the way we usually do it, but we could see equations as operations as well. So in this case, associativity is an operation which takes x, y, z, w and f, g, h, and provides us now with this ASOC proofs of the fact that these compositions are are equal. And the way we sort of represent this combinatorially is that we start with pure operations, which are operations where we don't depend on other operations. So, for instance, composition in categories, we see that this this context, the input for that is a purely judgmental context, which means that the only things which are in here are variables and judgment kinds, like objects and hom and so on. And then this can be represented combinatorially as a pre-sheaf on the corresponding category of judgments, where object would be mapped to the set XYZ, and hom would be mapped to hom would be mapped to the set FG, and then the arrow going from hom to object corresponding to the domain sends F to X and Y to and G to Y, and the codomains similarly would send F to Y and G to Z. And then this is the result type, the resulting output of this would be represented as an extension of that context. That's sort of something we can represent purely combinatorially. But there is more to this than that, because different operations can depend on each other. So let's say we had an operation which just creates an object called 1. Maybe this is the start of constructing the terminal object or something. But and then we have another operation which says that whenever X is an object, then we have an arrow, exclamation mark, going from X into 1. And this second rule depends upon the first rule. And it also, for this to make sense, we need to say how that our application of this rule makes sense. So here it does, because it occurs in a place where we expect an object, and in fact, 1 is an object. So that makes sense. So we need to take care of those two things. So in general, we get that the operations also form a well-founded category or an inverse category, and the arrows of the category represent applications. So for instance, for categories, if we imagine the equations also as operations, as in we had for the associativity, then we see that associativity depends 4 times on composition, because there are 4 applications of compositions inside when we formulate associativity. And left identity and right identity both have 1 composition and 1 identity. Think about them. And in addition to these, the fact that these are related, we also have to say how they are related by providing maps between the contexts. And the way this is done in Myott does it in a bit particular way, in that it makes a context where all the defined subterms, all subterms occurring, are part of the context. So every term which occurs is first introduced as a variable and then decorated with its definition. And the definition is always that it's some term applied to some variables. And those variables might again be terms, and thus we get constructed terms. We don't directly work with like trees, and they don't have to be trees. They can be DAGs of applications of rules. We don't work with syntax trees directly. So, for instance, we have this this rule here. This is not a variable, so this has to be somehow introduced. So we say that we introduce a variable y, which only purpose is that it is secretly, or not so secretly, declared to be 1 applied to no arguments. And then we don't have a term here anymore. We only have variables, but variables where we've constrained it to actually be defined to only be 1 term. And now, and this is because we want there to be a well-defined map from this. Well, first from the context here, but that's easy. That's empty, so that's something there. But then also from the conclusion, like we had in this diagram you saw in the beginning, where you had. Let's go back to that. Where this would, for this one object, this would be empty, but this would be the context where we added a single object, and the inclusion here represents this operation of adding that object number 1. And then when we apply it, we first have to apply all the arguments. There are no arguments, that's easy. But then we need to have something to apply the result in as well. So that's why we add this to our context. Let's jump back to where we were. Just check the time.
We have 7 minutes.
Great, that should be fine. Okay, so let's have a look at the specifying terms in Myott. This one. All right. So here we you can see it. Yes. So here's the specification for categories.
Maybe if you can make the font slightly bigger, that'd be.
Yeah, sure.
Oh,
is this better?
You.
Yeah. Yeah, so here we have the identity operation, the composition, left identity, right identity, and the associativity. And because we don't have hidden arguments, this gets quite noisy, like composition here with each of the 5 arguments. But I'm working on that. And we also see an example of so we entered this syntax, and Myott will automatically do the expansions of all the subterms into arguments and so on, so we don't have to do it. But if we wanted to do it manually, we could. So for instance, here we have the right identity, which then is an equality between C and F, where F is the map we started with, and C is the composition of the identity, or the with F, where the identity is again expanded as a subterm. That's all hidden under the hood if you don't want it. Okay, and this checks, for instance, like if we forget an argument to composition, let's see what it says then. And it says, you probably, yeah, judgment comp take 5 arguments, but 4 was given. Or if we switch them around, like put the B where there was supposed to be an A, then it gives us a detailed explanation of that, the arrow we did here. Okay. And then I wanted to show one thing from, let me just jump it here, easiest, from the API. There, sequence examples. Because like we saw in this in the specification, we had to write the composition, and then we had to give the object and so on. So at some point I will have implemented hidden arguments, but for the moment you could use the API to define your own composition operation, which manually looks up the A and the B and the C as using the dependency operations, for instance. So it's in theory, it's possible to infer the arguments. It's just not implemented yet. But But the idea is that we, once this is mature and usable for people, then they could extend the functionality by using the API. All right, let's do a quick note about rules and then wrap up. So the thing about rules is that they're sort of operations on the next level. They take up specifications of operations as their assumption, and they produce operations as their result, so to say. So for instance, when we bind variables in pi formation, it takes we can think of this as an operation specification, that if we have an operation which produces a type and an operation which every time we have an element of A, we produce a type B of X, then we produce a new type pi of that as an operation with no arguments. And because these things on top here are exactly the kind of signatures we had for operations, this also can be given a combinatorial representation. And in first order logic, similarly, we could handle quantifiers. So it's not restricted to just doing type theory. And there's a similar elaboration here as was with the operations, where we have to construct all the terms in the middle, where, for instance, when we use a pi type, we have to make sure that that's elaborated to an actual constructed rule when we reference this. But that's technical details. Rules in Myott are currently not, they don't have a syntax yet, but you can interact with them using the API. We go to examples, something like this. So for instance, here is the clear pi, which says that there's a rule pi, which takes parameters A and B, and it produces a type in the end. And then there are some utility functions for that, and declaring lambda and so on, application, so on and so forth. And then once this is done, we will also work on translations. Like I'll skip this for now, but the idea is that you can give a similar account of translations between theories, because now we have everything spelled out as kind of finite sets with extra structure on them, which would be more approachable to give a definition of translation, which can be actually worked on and be tamed a bit. Because if theories are just like sets of strings, then translations are just functions, and that's not very. It's hard to work on top of that. If things are finite sets, it's easier to sort of say what properties of the do we want of the maps we're giving. So where is this going? Well, all the theoretical parts need to be properly written down and elaborated, and we need parsing and checking for rules. And I want a kind of built-in notion of equations. So currently, equations are just the special kinds of, or not very special kinds of judgments, but that adds a lot of overhead when you have to specify all the rules for it. So it would be nice if some of that was handled automatically. Translation between theories needs to be worked on, and there are lots of usability things. So I want this to like now it's just a prototype, but I want it to be actually something one can use, which means that we'll need a module system, because you want, when you specify your theory, you want to import all the rules which already exist around, or make your own choice of the rules which exist, and you don't want to rewrite them every time. We need a module system for referencing rules of other theories, so that you can import them and use them and translate them and so on. And like you saw, there's lots of extra arguments everywhere, which should be inferred. I also have this idea, and I'm working with Mikhail Barash on writing grammars in an easy way of specifying grammars which use binders, because here there are lots of binding operations. And I would like to be able to specify custom grammars for each theory, so that you can write them in a way so that you can specify the grammar along with the specifications of the rules, so that when you write derivations in that specific theory, then you can do it in the most natural grammar for that, not some synthetic grammar constructed generally. And then we would like more liberal notions of rules, like binding arbitrarily many variables, for instance, which is needed for some type theories. Yeah, okay. I will not go into the leftovers. We don't have time for that. So yeah, that ends the talk.
All right, thank you very much. So we're gonna now thank Håkon for this great talk. Please join me. And now we're gonna open the floor to questions. So feel free to unmute your microphone at any point and ask the question, and we'll proceed. So I see a raised hand, so just unmute your microphone.
Hi. It's a wonderful talk. I love to see different ways to talk about theories in general. My question is about how to use such a system. So you haven't talked much about morphisms or translations, but I guess that's the way you would talk about, the category of certain algebraic structures, right?
Yeah.
But one problem that comes up when you do this is that, well, even if we often talk, live inside some category and talk about its objects and etc., sometimes we want to talk about multiple categories and relate them. So my question is really specific. How would you talk about functors, for example, in that category, that theory?
So I have actually played around with trying to define like a theory of categories and functors in this setting. Let's see if I can find. Not sure I have it in a good way written down. Let's see. I think it's. But yeah. So I imagine that you could. I mean, you probably if you do category theory, you probably don't want to work inside a specific category. You probably want to have the theory where the first judgment form is being a category, and then the second judgment form is being a functor, and then the third judgment form is being a natural transformation between those functors, and then equality between natural transformations, and probably something like Kohn extensions or something, a judgment form for Kohn extensions to define various categorical notions. But I haven't worked on the details of that, but that's something I can imagine one could do.
Okay, thanks.
Yeah.
All right. Any other questions?
I think this was mentioned in the chat at some point. Could you say something about how this theory is related to classical logical frameworks? Because it seems very similar to just defining a dependent type theory as your framework and doing stuff in there.
Sure. Yeah. So the logical framework is like for instance, deducti is an implementation of that. So that's like a bare bones type theory where you have pi types and nothing else, and then you add on top of that, you assume that you have elements and so on. The relationship to that is that here we are slightly more restricted in what we can do. We don't have general pi types work with. We can't do arbitrarily high higher order functions. We can only sort of do functions at the second level. We can have functions as input and give functions as output. But the main difference is that the logical framework is very syntactical, while this is more combinatorial and a bit more restricted, so that hopefully it will be easier to get a nice notion of translations between these kinds of theories. That's the hope. And it will be easier to work with translations between these theories. And yeah. Does that answer your question, or?
Yeah, basically.
Yeah.
So it's sort of like a second order dependently typed theory instead of a higher arbitrarily higher order
from a sort of very
point.
like user perspective, that's what it is. Yeah. And then under the hood, it's working more with like finite set representation of things.
Can I have a question?
Yeah.
Yeah. So you said that for future work, you want to have some equations and reductions. So what did you mean by reductions? Did you want to have some sort of a normalization algorithm behind that to reduce?
So in general, we can't have a normalization algorithm for anything you could specify. So we can't do that in general, but we would. It would be nice to that if you specify reductions, that it would try to rewrite using the rules you specify and see where it's going with that. That would be one. Yeah, it would not necessarily normalize, but you could have reasoning about confluence like you have in deducti or.
So basically, you would use the equations you specify as an operation, or however you do that now, as a basis for your reduction. Is that?
Exactly.
That's the idea. Okay.
Yeah.
Thanks.
Okay, Chaitanya.
We can't hear you.
Somehow you're unmuted and we can't hear you. It's the worst of both worlds.
Yeah.
You're supposed to be muted, but also when you're not.
Chris, maybe you can read her question from the chat because.
Oh, is it going to be the same question?
How about now?
So, oh yeah, we can hear you now.
Yeah, I know there's some issues with my mic.
Oh yeah, I see his question, and no, that's not a requirement. So the question is that he noticed that the types of variables in all the context and all the examples are pure in that they don't contain any terms as arguments to their types or sorts. And he asks if that is a requirement. That's not a requirement. So the context can have expanded terms. Yeah.
So my follow-up to that would be, have you thought about the difference in expressivity between allowing and not allowing?
You are unfortunately too low volume for me to hear you.
Have you thought about the difference in expressivity between allowing this and not allowing this?
So I briefly thought about it after your talk in November, but I wasn't able to decide if that's if you can always rewrite a theory to one which has this pure. So I don't know actually, and that would be a really interesting question which we could think about.
Okay, thanks.
Yeah. The background, I guess, for your question is that yours and Peter's notion of dependently typed operand has this requirement.
Yeah, exactly. Yeah.
Yeah.
I have a question as well. Hi, Håkon.
Yeah. Hi, Jacopo.
Thanks for the very nice talk. So I was wondering, I guess this is part of what has to be written down yet. But I was wondering about the correspondence between the signatures in Myott and the signatures in Folds. So how precise correspondence and
so the judgments are purely the kinds of signatures you have in Folds. So and then we have this operations and rules on top of it, which Makkai, he does without operations. He uses he has first order logic on top of this, so he can specify like unique existence instead of using operations. We don't have first order logic put on top. You could specify it, but then you would use the rules and operations to specify first order logic and not vice versa.
Okay, I see. And well, you mentioned translations between theories, and I guess this will correspond to some sort of morphism between signatures in Folds as well. Is that true?
Well, not exactly. So you have the notion. You have a notion of morphism between signatures and Folds, but and those would be still translations. But you would like to have derived. You want to be able to send a specific judgment to a derived judgment. For instance, you want to be able to send, let's say, being a set to being an element of a specific set in type theory. For instance, if you translate the set theory into type theory, you would want to be able to send there's a derived judgment being an element of your type with model set theory.
Yeah.
So you want to be able to send judgments to derived judgments. So it's a more complicated notion.
Okay, but do you think you would be able to express that using the language of Folds?
So that's the hope that we can, elaborate this down to the language of Folds.
Well, I'm looking forward to your paper on this.
Me too.
A lot.
Hey, I have a question about binding. So it was not clear to me where you specified in your signature for type theory that in type theory we do have term variables, but we don't have type variables.
Yeah. So currently that's not specified anywhere. So you can have in your context when you specify your rules, you can have types as part of that context. But when you specify, like for instance, pi types, you can only bind over elements of another type. So you can't do but that's a consequence of the rules you give, not with the underlying theory, because there's no fundamental difference there between.
And do I understand this correctly that this possibility of binding in the signatures, it's already there in Makkai's framework, or is this something that you added to the Makkai stuff?
So this way of specifying rules which allow binding is something we've added to this. Yeah. So he has binding operations like in when he specifies for all and exist and so on. It's the same kind of binding, but in general, yeah.
But for him, it's in the logical part, so it's in the first order logic and not in signatures.
Yeah. Exactly. Yeah.
Yeah. And I just wanted to point out another. Yeah, thanks. So I just wanted to point out another related way to specify signatures, which is quotient inductive types, so QIITs. I gave a talk about them at HoTT a couple of months ago, where you can also it's just another way to write down GATs in a more syntax independent way, and you can also they also support bindings.
Yeah. Cool. I'll check that out. That sounds cool.
Thanks.
All right. Further questions or comments? Let me give everyone a few more seconds.
Maybe one last question.
Sure, go ahead, Tanya.
Have you wondered about what a linear operation might be?
I wondered about it, but I don't have an answer. So it somehow it would require that our functions are injective at some point. Yeah, that's something I would like to have a look at. You probably have more insight to that than me. But that's a great question.
Or maybe just, have you thought about trying to describe it a little more abstractly, saying something like it's a judgment you have some judgment in the context gamma, such that gamma is somehow terminal among contexts in which you can judge your judgment, or some substitution of your judgment, something like that.
So I haven't thought in that direction. It sounds interesting. We should talk about it. Yeah.
Thanks.
I guess there's one big question. Where does the name?
So at the
Myott
moment,
come
it's just a name, but originally it was make your own type theory.
Well, Peter pointed it out in the chat, but yeah.
Yep.
I was wondering if that meant something in Swedish.
No.
That's what dependent
It's a
type
fun
theory.
word.
How
Yeah.
dependent type theory is in Swedish. Yeah. Okay. Okay. Any other questions? So far, it seems like many joint projects will come from the questions following this talk. So if you want to get on the paper with Håkon, ask now. Okay, I hear no more invitations to write joint papers. So let's thank Håkon again for this great talk.
Thanks everyone for nice questions.
And that's it for today. HoTT will return in 2 weeks with Egbert Reiche.